So, today I need to talk about some group theory, basically. And the reason for that, essentially, is that as we study number theory, all the time we're, it's a good thing to study here because a lot of what we're looking at really is touching on group theory. So I think it's wise to talk about, in particular, we're going to talk about cyclic groups. But in order to do that, I have to start back and just start at the beginning, right? So definition. G with star, right, is a group if what? One, A star B is an element of G, right? For all, I don't even like to say it that way. Let me say it like a slightly different way. Oh man, where I put my eraser? Hid it in my office. Just a second, I got to get my erasing shirt. I've opened some new markers because my markers in algebra this morning were getting kind of sad, and I can't do this class with sad markers in good conscience. It's just not right, Okay, so some fresh markers. All right, so I think it's easier to get across the idea by just saying that A comma B maps to A star B in G is function, right? It's a function from G cross G to G, right? The operation of the group, it defines a function, right? Two, A star B star C makes sense, right? So in other words, you have associativity. And what else? Three, there exists E in G such that X star E is equal to X is equal to E star X for all group elements X. And what's the fourth axiom? Right. For each A in G, there exists A inverse in G such that A star A inverse is equal to E is of course equal to A inverse star A. Now, to the logical purist, of course, this definition that I've given is an anathema. I mean, it is very clumsy and heavy-handed. You can cull this down much more. It suffices to define a left inverse. Like associativity and the other stuff to play with here will allow you to prove the existence of a right inverse. Like, this is not a logically minimal definition by any stretch of the imagination, but it's a pedagogically useful one, so that's what we'll do, all right? And so I would add 5 to this, right? If A star B is equal to B star A for all A, B, and G, then what? G is an blank group. What fill in the blank for me? Abelian. Very good. Abelian group. So we have that. Now, first things first, the notation. Let's talk about notation. all right? So if star is an addition, right, then typically notation we use is A star B is equal to A plus B, all right? By common human decency, it is assumed that if you use addition, it's a commutative group. It's an abelian group. Now, there exist perverse abstract algebra books which will talk about non-commutative addition, but no, just no. Like it should be a custom. Addition is commutative. All right, so A plus B should be equal to B plus A, right? Okay, that's in a custom that I assume typically in my work. Now, if star is multiplication, right, then typically we use the notation A star B is equal to AB, right? So this notation on the right-hand side is also known as juxtaposition, right? Juxtaposition is a very nice notation for an operation because it's, well, really easy to write, right? But of course, the absence of the multiplication will make proving certain things kind of a drag, right? Now, so you have addition, you have multiplication. These are common operations, right? Can you think of any other kind of operation of a group that you saw in your abstract algebra course?
An operation?
Yeah, what's another? How about this? Star is...
Division?
No, division won't do it, no.
Yeah. There was dot.
Dot?
Just for multiplication.
Well, so yeah, but the other, in terms of native examples, a good example would be composition.
Oh, yeah, we did.
I'm sure you talked about that. Composition of functions, right? Then typically A star B is denoted A circ B, right? Now, all three of these appear in your homework, all right? Okay. So next order of business in terms of notation is to, well, let me just sort of give a foreshadowing comment. Just let me just get right to it, okay? So here's some examples of each case. Addition, that for us is going to be, for the most part, Zn. That's an example of an additive group. Integers modulo n, additive group. All right? Now, un, which we'll talk about today, is a multiplicative group. The un is constructed using the multiplication modulo n. All right? And then finally, an example of using function composition would be aught of Zn. Now, aught of Zn, this is the set of so-called automorphisms. So those are actually isomorphisms from Zn to itself. Isomorphisms which preserve the product, the additive product. All right? So those are all examples of groups. Okay, so so notation, right? So we need to talk about powers. Powers that be. What kind of powers do you got? Well, for addition, right? First of all, we write minus a plus a equals to 0, right? So minus a is the inverse for an additive group, right? For multiplication, which I'll write like this, we have, of course, a inverse times a is equal to 1 typically, right? Well, I debate. I'll go with e in here for a while, but for the, I mean, let me go with e in the abstract. I'm going to go with e as the abstract identity, but it is true that the identity, so the additive identity in Zn is really like 0, right? Which you could do this, which of course you could just write 0. And in here, the multiplicative identity is really this, which you, of course, could write that. And you could also just drop it all together and understand that you're working modulo n, and we do that. All right, so first of all, just be aware, additive inverse, multiplicative inverse, right? Both group inverses, but different. Now, how about repeated addition? A plus A, what's that equal to? A plus A is equal to 2A, right? That's a definition. On the other hand, A times A is equal to A squared, right? That's actually a definition. And let me give you a sort of a recursive definition here. A plus NA, right, is by definition what? 1 plus n, right, times A. So that's how we would recursively define addition, right? Multiples, if you will, multiples of A. In the additive case, we have multiples of A. In the multiplicative case, we would do something like A times A to the n is equal to A to the 1 plus n, right? And both of those definitions would be recursive definitions for, powers of A, right? And to start with, I'm thinking of n as being where. So for here to start with, we're thinking of n as being a natural number, right? I guess I should also mention, to get the recursion starting, we probably need to know that 0 times A is equal to 0, right? And A to the 0 is what? 1, right? Or in this case, E. If I'm sticking with E as the multiplicative identity, as I'll try to in this lecture, okay? Now that just covers positive powers, but do we also define negative powers, right? So what do you mean by negative multiple of A? How would you define minus 3A, for example? It's minus A plus minus A plus minus A, right? Just repeated, it's a multiple of minus A. And repeated, and like a negative power is defined to be the power of the inverse, right? Okay? So that's how we define powers or multiples in a group. Once you make those definitions, you can prove the following properties. Theorem. In additive, like in additive G with an addition, have NA plus MA is N plus M times A, right? And in a multiplicative group, we have what? A to the n times A to the m is equal to A to the n plus m, all right? These can be proved from the recursive additions. There is more here than you realize in terms of actually proving it. There are some subtleties here. If you really try to prove it carefully, you will find these subtleties. If you want to see these subtleties dealt with and not tucked under the rug like so many books do, a good place to look is Rotman's. Elementary. I forget the exact title, but it's as elementary abstract algebra book. So if you don't know, Rotman is an incredible author. The depth of his writing, it's hard to overstate. You can learn so much from Rotman. His books are really masterpieces. So much history and meaning of words and things like that. For example, in Rotman's books, you'll read things like, what is mathematics? How many math classes have you had? Do you know what mathematics means?
The study of like logic.
It's a classical Greek word which means to learn.
Mathematics.
Yep. Do you know what theorem means?
A stated thing with axioms.
See, that's functionally what it is, right? But what it actually means, the word, essentially is, this is important. Pay attention to this. That's what theorem means. Corollary is from the word called flower. Yeah. It's literally something that's growing out of the theorem, like a flower, a gift that you would have given in ancient grease or whatever. These are the kinds of things that are in Rotman's books, you know. Things you wouldn't expect, like joyous things. Anyway, these are the laws of exponents, right? Okay, great. So let me talk about our examples. First of all, we have Zn. So here we're talking about, you know, 0, 1, 2, dot, 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 n minus 1, right? Which I'm using that as a shorthand for these guys, right? So technically, if you want me to be fussy here, like x is really equal to x plus nz, right? Or if you like nz plus 1, I mean plus x, whatever. My point is I'm not going to write that. I'm just going to write this for, you know, that, okay? So you can prove that that is an additive group because the addition is commutative, it's associative, and there's an additive inverse for everything, right? It is a group. Addition modulo n satisfies the axiom of group. That's example number 1. Example number 2, un. Whoa. Is going to be equal to, here's how it goes. X in Zn, and I gotta clutter this up a little bit just to make life easier, all right? So I'm going to use the bar notation. Actually, I'll actually use the bracket notation here for just a second, okay? Because I need to not use the bracket notation when I write next. So it's the equivalence class is Z mod n such that the greatest common divisor of x and n is equal to 1. So some other books will also call this Zn with like an upper X. It's the multiplicative, well, we could say it this, I should say it this way. It is the group of units in Zn. The group of units in Zn. That's kind of more clear from this notation over here. So you could also write it U of Zn, and that's part of a more general system of nomenclature where you'd say like units of a ring. All right, this ring happens to be Zn. A ring, as we'll talk about later, is a set with an addition and a multiplication. Of course, we know Zn has addition and multiplication, as we proved. Now, my claim is that that is a group. All right? My claim is that un paired with multiplication modulo n is a group. Let's prove it, okay? So we should do that. Did you actually? You probably. I bet I would be shocked if you didn't do that in your modern abstract algebra course. Like, yeah, I'm sure you did that. But doesn't hurt to review, right? Let's see here. So, come on, get out of there. Get out of there. You will get out of there, sir. Come on. Okay, so first of all, I'm going to erase this as in the way. Proof that it's a group. Okay, so let's observe that multiplication in Zn is associative, right? And commutative, right? Not that we need commutative, but it is, right? And this thus the set equivalence class generated by 1 is multiplicative identity, right? Now, the question, though, is what if we take, well, the question is what about closure? If we take the product of two units, is it again a unit? And how about the inverse? Is the inverse of a unit? Okay? So let's deal with closure first. Let let's say x and fine. This is often what I find. To make proofs like clear, I have to use the cluttered notation, you know? So let bracket x, bracket y be elements of un, all right? Then what does that give us? That gives us that the GCD of x with n is equal to the GCD of y with n is equal to what? Equal to 1, right?
Yeah.
Did I ever set the, I'm not sure I actually set the zoom length here. Hope I haven't been all fuzzified this lecture. That would be sad. Well, anyway, what's done is done. Sorry if you couldn't make it today. Half the class is missing, you know? Okay, so GCD of x comma n, you said 1, right?
Yeah.
Great. So then what does that entitle us to by Mr. Bazoo's theorem there, right?
Yeah.
By Bazoo. There exist, let's see here, A, B, C, and D in the integers such that AX plus BN equals to 1 and CY plus DN equals to 1. By the way, there may be a simpler proof just using like elementary divisibility, but I don't even think about, I'll be honest with you, Audric, like when I'm proving something like this, I just write down Bazoo's theorem and hope it happens. Like, because usually it does. Thus what? Huh. I mean, I want to show that xy is a unit. Can you see how to get something like xy times something plus something times n equals to 1? I mean, if we could fill in those blanks, we'd be peachy. Oh, here's a step. Yeah. AX is equal to 1 minus BN, and AY is equal to 1 minus DN, right? CY, rather. So AX times CY is equal to 1 minus BN times 1 plus 1 minus DN, right? What does that give us? Well, it gives us 1, right? Plus n times what? We got ourselves a minus d minus b plus bdn, right? Rewrite that. What does this give us? Thus, AC times xy, right? Plus n times d plus b minus bdn is equal to 1. That actually implies, right, that the greatest common divisor of x, y, and n is what? Is 1. If you can write a linear combination, integer linear combination equal to 1 of two integers, then that implies that those two integers have a greatest common divisor of 1. This is part of the whole Bazoo business. Think about what would happen if let's see how to say this. Well, anyway. So what does that show? Well, that shows that xy is what? Xy is an element of un, right? Because it satisfies the defining condition. So that proves closure. There is another way to argue this, which I'll mention just in case there's a gap in my current argument. The other way to the other way to argue is just like, okay, if x and y are in un, that means x inverse and y inverse exist, right? So you could easily check that. So if this is the case, then x inverse and y inverse. That's not how I want to write it. Excuse me. My bad. So, anyway, do you have this? Do you have this?
Almost, yeah.
Oh, okay. What I'm about to write down is just like, if we know that x and y are units, then the product is also a unit because of the sock-shoes formula.
Oh, yeah.
Because we can definitely construct the sock-shoes formula just if we have inverses existing, right? So if you take y inverse, well, it's commutative, so the sock-shoes can be like shoes socks, When putting on your socks and shoes commute, it doesn't matter which one you do first. So, it's kind of abstract, a little bit abstract about that, but yeah, I mean, alternatively, you could say this, well, xy inverse is nothing more than, in this context, x inverse, y inverse, because, well, they commute, so you write it that way. And if you multiply that by xy, of course, you get back 1, which proves then that that it's closed under multiplication. But I think this argument's also good. But this is also very reminiscent of like our proof that the modular arithmetic was like with the transitive of the equivalence relation. I think similar to this calculation. Okay, then what's left? What's left? So we proved that it's closed under multiplication. What's left?
Identity, inverse,
Inverse. So let x be an element of un, right? Then by Bazoo, there exists a and b in the integers such that what? Ax plus bn equals to 1, right? Since the GCD of x and n is 1, right, by assumption. We get that. But this implies that the equivalence class defined by A and the equivalence class defined by X is equal to the equivalence class defined by 1. See, because when I take the equivalence class of this, the one with n drops out because we know multiples of n get absorbed into the equivalence class by our work in the previous class, right? So that just simplifies the equivalence class of A times equivalence class of X. But that implies what? The equivalence class of X inverse is, in fact, nothing more than this one right here, right? But, but X was arbitrary. Therefore, the group of units is closed under inversion. So it's a group. So the group of units is a group. All right? Can I erase? Cool. Now, what else do we talk about in group theory? I mean, there's a lot of different things, but one of the things we like to talk about is the order of the group, right? Definition: the order of G is equal to n if G is finite and has n elements, right? Otherwise, the order of G is what? Infinity, right? Otherwise, it's an infinite group. It's either a finite group or it's not. Okay. Now, the definition, the order of UN, right? What is this equal to? This is equal to the size of the set of, it's the size of the set X in the integers such that what? Well, it's not X in the integers. That's too much, right? We don't need that. We should say, I mean, I guess we could. I can put more conditions over here. So I'll say such that the greatest common divisor of X and N is equal to 1, and 0 less than or equal to X is less than N. So it's, and I, just to close, I'm saying the size of that is the order of UN, right? This set that I put there, that's not technically UN, right? That's a set of integers. So that's a set of representatives for UN, sure. But of course, this has a name. This is called the phi of n. So phi of n, order of UN. This is the Euler phi function, sometimes also known as Euler's totient function. Right? This is a lot of the reason that we're even talking about groups in this number theory course, right? Because, well, this Euler phi function actually comes up in some important theorems on modular arithmetic, as we'll see. All right. Now, so some special cases, right? So example, let's see here. What if n is prime? What's phi of p equal to? Well, how about this? N equals to, let's say, 5. So we'd be looking at, Z5. It's got 0, 1, 2, 3, and 4, right? So U5 has what? 1, 2, 3, and 4. It doesn't include 0. So Z5 is order 5, but U5 is order 4. So it's not P minus 1, because you lose 0. Taking a look ahead, a ways ahead in this course, Z mod a prime is actually a field, because the only non-zero element, excuse me, there is no non-zero element, which is not a unit. So that's when P is prime. How about like a prime squared? What would we get then?
Prime squared.
Like a P next example here. How about like phi of 25? Oh, let's say something simpler. 9. That's phi of 3 squared, right? So what's Z9 have? Z9, you got your 0, 2, 3, 4, 5, 6, 7, 8, right? Which of the representatives of those is relatively prime to 9?
3.
Relatively prime. 3 would not be relatively prime.
Relatively prime, 9 and 2.
No. Relatively prime to 9, 1. Like 1 is always going to be in UN. get the idea.
Relatively prime mean like you multiply them together to create a prime number?
No, relatively prime means it has no, two numbers are relatively prime or co-prime if they have no common prime divisor.
Oh. 2.
Uh-huh. In other words, the condition is, what is the greatest common divisor? Which of these has greatest common divisor of 9 and itself being 1? Like you said, 2, 4, 5, 7, 8, right. Okay, so that's 3 squared. Let's look at 5 squared. What's phi of 25? So by the way, what did we just figure out? What was phi of 3?
6 plus 6.
Yeah, 6. There's six elements in the group of units there. So U25, what'd you got in U25? I'm not going to, here, I'll write out Z25, check it out. This is how I'm going to write it. 0, ... 24. There you go. Sorry, being a little bit lazy with my,
What's co-prime in there?
yeah, what is our U, what does U25 look like?
What is in there for sure?
Yep, 1. I would point out 1, 2, 3, 4, right? 5 is out.
5 is out.
And then 6, 7, 8, 9, right? 10 is out.
11's in.
Yep, 11, 12, 13, 14. 15 is out because it's got the common factor of 5. 16, 17.
18's out.
18's not out.
3.
25. You got to have a common factor of 5 or 5 squared in this here game we're playing. My apology. I did not move the camera. My bad. Okay, 21, right? 22, 23, 24, right? So what's missing, right? What's missing are the 0, the 5, the 10, the 15, the 20, right? So how many is that? That's 1, 2, 3, 4, 5, right? So phi of 25 is equal to 25 minus 5. And now that you see that, if you go back and look at what we had before, maybe you see that what we're missing here is what? 0, 3, and 6, right? So that's why we had 6 things there, because 6 is what? 6 is 9 minus 3. And so the story goes. This is the theorem. We can extrapolate from this, counting here. Theorem, if p is prime and p is greater than or equal to 3, then the Euler phi function of p to the power, let's say, n, is equal to p to the n minus p to the n minus 1. I guess to really, I mean, both of my examples were for a square, right? So I guess to really be convincing, we should look at like 27 maybe, right? Let's look at 27. How about Z27? So in other words, n is equal to 3 to the third power, right? So if you look at U27, what you got? You got yourself a 1, a 2, you lose 3, right? 4, 5, you lose 6, 7, 8, you lose 9, 10, 11, you lose 12. Well, yeah, but the thing is, if there's a multiple of 3, right, if 3 is a divisor of x,
Yeah.
the greatest common divisor of x and 27 is not 1,
Yeah.
it's 3, or at least 3.
Yeah.
So I have to avoid multiples of 3. Now, avoiding multiples of 3 automatically helps me to do what? Avoid multiples of 9, right? And so the story goes, 13, 14, 15's out, 16, 17, 18's out, 19, 20, 21's out, 22, 23, 24 is out, 25, 26, and then that's it, right? So that's U27. What's missing? The 0, the 3, the 6, the 9, the 12, the 15, the 18, the 21, the 24. How many numbers are multiples? How do you count the number of 3 multiples in 27? Think about it. You do, if you want. Here's an easier question. If you got 500 numbers,
Yeah.
500 consecutive numbers, how many even numbers?
Half.
Right, you just divide by 2, right? How many multiples of 3? Divide by 3. Good.
Gotcha.
So we just do 27.
Divided by
It's 27 divided by 3, which of course is 9, right? So in short, phi of 27 is equal to 27 minus 9, which of course is 3 to the third minus 3 to the squared. So that's why we get this p to the n minus 1, generally speaking, even though, of course, we had subtract p in the n equals 2 case. But generally, it's pn minus 1, because that's how many multiples of a p that appear in the list of 0 to pn minus 1. So there you go. There's your Euler phi functions. Well, excuse me. All I've done at the moment is showed you how to calculate the Euler phi function of what? Of a prime power. And I haven't even told you about 2, have I?
No.
There was a reason I said p greater than or equal to 3. The way it works out for 2 is a little bit different. Should I finish this story here while we're on it? I guess I should. Actually, this is not the finish. This is not the end of the story. We need more group theory to get the end of the story. Truth be told, when did you wake up this morning?
4 a.m.
4 a.m. Ay, ay, ay.
Yeah.
Ay, caramba.
I'm usually teaching at this time.
Ooh. Teaching.
My coffee's my car.
Oh,
And this is not the usual day we do number theory.
that is true.
So I blame it on you.
I blame it on the hurricane. Blame it on me.
You can blame it on whatever, but I can blame it on you.
That's fine. I'll take the blame. Doesn't earn you anything, though.
No, that's fair. Satisfaction.
Come on. I got my curses. I don't remember these formulas right off the top of my head. I don't want to say it wrong. I mean, we could work. Tell you what. Let's discover it. Let's discover it. Let's work it out. So, all right. Here's the example. Z2, right? Then U1 is very boring. It's just 1, right? So phi of 1 is 1. Z4 has U1. What numbers are relatively prime to 4? 1 and 3. Right? So the Euler phi function of 2 squared is equal to 2. How about Euler phi function of 8? What's Z8? What's U8 equal to? 1, 3, 5, 7, right? So that means Euler phi of 8 is, or Euler phi of 2 cubed is equal to 4, so that's 2 squared. All right. How about, the trouble with 2 is 2 times 2 is 2 plus 2. So It's not. 2 is troublesome. Z16. What numbers are relatively prime to 16?
Everything not 2.
Everything not 2. So you got your 1, your 3, your 5, your 7, your 9, 11, 13, 15? So all the odds, huh?
Yeah. That's what I was getting at.
So that one, phi of 16 apparently is equal to 1, 2, 3, 4, 5, 6, 7, 8. So what's
And that's 2/3 cubed.
that's 2 cubed, yeah.
2 4 to the 4, so you go to 2 cubed.
I was just looking at this a second ago. It is in here. I've lost track of it. You need to stop yawning. It's catching on me. You know, like you're
Nazi jokes.
you're influencing me. Let's see here. Where was I? Euler phi function. Let's see here. Let me look this up. I don't want to say it wrong.
I just hope I can read my handwriting.
Ah. Okay, I was just on that page. Great. Really helpful. Dude, come on. Come on. Out with it. Sorry.
You're good.
Ah, okay. So I think generally Euler phi of 2 to the n is 2 to the n minus 1. That is for n greater than or equal to 3. I think that checks with what we see here, right? So now, of course, in the case of 1, in the case of, I'm an idiot, look at this. That's supposed to be 2. Yeah, 2 is 1. Phi of 1 we don't talk about. So phi of, well, looks like it worked for n equals to, I think it works for n equals to 2 as well, doesn't it? And n equals to 1. I think that just works for n, doesn't it? Because if I put in n equals 1, I get 2 to the 1 minus 1, which is 2 to the 0, which is 1. Yeah. So.
Yes.
And
No, 2 to the 4, 2 to the 3rd. No, you're right.
yeah, and I think the reason for this is pretty simple actually, because 2 to the power n, what numbers are relatively prime to like 2 to the power n? Well, all the odds. So you divide by 2, and 2 to the n over 2 is 2 to the n minus 1. Interesting. Oh, okay, never mind. I'm getting distracted by. So there's a counting the number of units is easy, right? I should say it's easier than understanding what the actual structure is of the group of units. See, that's a different question. As we're looking at a group, we can ask the question, how big is the group, right? That's a somewhat easy question. You just count the number of things, right?
Yeah.
But then on top of that, you can add additional questions like, is it commutative? Is it a abelian group, right? Is it? And then you can add other kinds of group characterizations and ask, does that group we're talking about have those characterizations, right? I can't really say any character. I haven't introduced any other characterizations yet other than abelian, so I'm kind of stuck by be a little fuzzy here, but anyway. Okay, so next up, we should talk about subgroups, right? So if G is a group, right, and H is a subset of G, and H is a group with respect to restricted operations of G, then H is subgroup, right, of G, and we write H less than or equal to G. Okay? There is a very nice subgroup test, right? Let me remind you that, the subgroup test theorem. What was that? What was the subgroup test theorem? If H is a subset of G, and A comma B, an element of H, implies A inverse B is an element of H, then H is a subgroup of G, right? So I'm assuming a multiplicative context, right? What would this look like if we were stating the theorem using additive notation? It would look like this, right? I mean, you could do AB inverse if you want. Let me do it that way. So like additively, what would this look like? If we were doing for additive group, the subgroup theorem looks like what? A minus B is an element of H, right? If we were in an additive context, that would be what we were checking. And there's something else I need, right? What was the precursor, the preamble here? If H is a subset of G and H is non-empty, right? Yeah. You need non-empty. Non-empty subset closed under this, right? So that's the subgroup test theorem. Can you tell me, sometimes we don't look at it like this, we instead look at it like what? You could also look at it as two things, right? You could check that A plus B is an element of H and that minus B is an element of H, right? You could check those two conditions separately. That's another version of the theorem. Or in the multiplicative case, you could check that AB, it's closed under multiplication and it's closed under inversion, right? This one, you could also have checked that AB is an H and that A inverse, or well, I'll say B inverse is an H, right? If you have both of those conditions, that's another version of the theorem, right? Now, what's the best way to prove something? I think it depends on like the particular subgroup, like which is the easiest version of the theorem to use, whichever one's more natural. It's kind of up to you, right? Okay. So, definition. If G is multiplicative, then, and of course A is an element of G, right? Then this thing here, angle bracket A, is equal to what? This is equal to A to the power n, such that n is an integer. So for a multiplicative group, the set generated by A is powers of A, both in the positive and negative sense. Now, if G is an additive group, right? And let's say X is an element of G, right? Then this thing is what? What's the set generated by X in that case? Well, then it's multiples. It's multiples of X. So it's NX, such that N is an element of Z. In either case, if H is equal to the set generated by A for some A, then H is called a cyclic subgroup of G. Now, I guess that's kind of bad mathematics, right? I've put the cart before the horse, so to speak. Like, usually we do what? Usually we prove that the set generated by A is in fact a subgroup, right? So, how are we going to do that? So, I mean, this is a theorem. The set generated by A is a subgroup of G for any A and G. It doesn't matter if it's an additive group or a multiplicative group, either way, subgroup. So the proof looks something like this. Notice that 1 is equal to A to the, I'm going to give a, so in this kind of context, it's traditional to do proofs in the multiplicative notation, right? Because at least there you're not assuming commutativity. Like if you do an additive proof, it's kind of But it is also understood that all the proofs we do in multiplicative notation equally well transfer over to the additive case, right? This is part of the beauty of the abstraction here, is we give an argument for a group, it holds for both kinds, multiplicative and additive groups.
So for Z, H, if A, like, A is 2N,
I should say E here. What's that?
like, we're talking about a cyclic group for all the, like, a subgroup of Z would be, like, all the multiples, or not the multiples, all the...
Oh, you're asking what are the cyclic subgroups of Z mod N? Yeah, that's a question we can ask. We'll get there in a minute.
Okay.
We're not there yet. So A to the 0 is E, right? And so that's an element of this, right? So that's non-empty. Let X and Y be elements of the set generated by A. What's that mean? Then there exist M and N, right? Integers such that what? X equals to A to the M, and Y equals to A to the N, right? Then X, Y inverse is equal to A to the M, all right, times A to the N inverse. Now, if you have more patience than I have today, you can prove that the laws of exponents work for the recursively defined powers that we have. In other words, this simplifies is as we would in intermediate algebra, M minus N. But the thing is, M minus N is an integer.
Yeah.
Therefore, that is an element of the set generated by A, right? Therefore, by the subgroup test theorem, thus, the set generated by A is a subgroup of G.